Jai Hind to all. This is Dr. Shivani Agarwal. Today's my topic is the virtual memory. This is a topic of the operating system. So let's start the topic. What is virtual memory? Virtual memory means we have a storage mechanism that creates the illusion in front of the user. That memory does not exist, but it is exist for give the solution for the better solution for the large programs. Actually, the user always in the myth place that it is a storage mechanism that we have to place the process in a large big memory. But in virtual memory concept, the user can store process with a bigger size than the available main memory. That means the size of the main memory is lesser, but we store the process or bigger size process in a small main memory. So this is the basic concept of the virtual memory. So it gives the illusion in front of the user that we have a sufficient memory for storing any size of the process. But actually the concept of the virtual memory generates by the demand paging concept. Actually, we deal with the secondary memory and we have to create the space from the secondary memory. So this is a part of the secondary memory as the main memory. So we store a large amount of process or large size of process stored in the main memory when the main memory is the small in size. So this is the basic concept of the virtual memory, that it creates the illusion in front of user that any size of program we have to save in the main memory when the program size is larger than the size of the main memory, but we have to create the space in the main memory for that biggest process. This is how we have to do this. We have to do with the concept of the virtual memory. So basically, what is the concept of the virtual memory? How we have to do this? So how it is possible basically? So virtual memory is a space where large program we can store, that I already explained, that we have store large program, the size of those programs are higher or bigger than the size of the main memory. So we actually does not save the complete program at a time, but we load the page in front in sequence of the process. So we save only the pages, or say that the portion of a process, that process size is bigger than the size of the main memory. So this is the concept of the virtual memory, that we have to store any size of program, that program size is bigger than the size of the main memory. So we don't load a single process in the main memory. Instead of the single process, we load small pages of the main memory, small pages of the process into the main memory. So this is the concept of the demand paging. Which page demand by the user, then those pages saved in the main memory instead of the complete process. So this is the basic concept of the virtual memory. Now, what is the biggest problem? Biggest problem is this: if the process is not fitted into the main memory, then how CPU can access the data, because we can't find the physical address of that particular page from the main memory. So the solution is that this problem we have to solve by using the concept of the virtual memory, because virtual memory follows the concept of the demand paging. We can't store or load the complete or the whole program at a time, but we load pages into the main memory. Now this is the basic concept, how we have to save the page. That page you have to demand it. Actually, this diagram shows this is the secondary memory. In the secondary memory, we have the 4 processes: P1, P2, P3, P4. Each and every process has 4 pages. That is, these are the pages P1, P2, P3, P4, and each page has each process has 4 pages. This is suppose P0, this is P1, this is P2, this is P3. So these pages represent that P0 of P1, P1 of P1, P2 of P1 and P3 of P1. Instead we take the name as P0, P1, P2, P3, we take A0, A1, A2, A3, suppose A1, A1, A2, A3. So these are the 4 pages in a process, that is P1. These same as P2, P2 has also stored the 4 pages A, B0, B1, B2, B3. Same as P3, P3 also stored the 4 process, that is C0, C1, C2, C3. So this concept known as that we have a 4 process in a secondary memory and each process has 4 pages. So correspondingly we have to store these pages into the main memory instead of each process. So actually we don't store the complete process in a time, because these process size maybe these process size is bigger than the size of the main memory. So how we have to store each and every demand of the user, or how we have to solve each and every demand of the user. So this concept belongs the virtual memory concept, or it is known as the demand paging. So in the main memory we have two things, that is the frame number and the main memory number. So in F0 first frame, F0 store the operating system, F1 store page 0 of P1. This is not the complete process, it is an individual page, that is page 0 of P1. Now F2 store PMT. What is PMT? Basically it is the page map table. Each and every process has the individual page map table. So we have a page map table of P1, we have a page map table of P2, similarly as P3 and P4. So we have each and every process has the PMT. These PMTs are also stored in the main memory. So this is shown the page map table of process P1. So in this table it is right that page table of P1. So this table shows PMT of P1, PMT of P1. Okay. So frame 1 and frame 4, frame 1 and frame 4, frame 1 and frame 4. This shows the valid bits. If it is 1, that means any page of process P1 stored in the main memory in frame F1 or F4. F1 is stored with the valid bit 1 and F4 is stored with the valid bit 1. That means two pages are stored in the main memory and these pages stored in the position of F1 and F4. And these 2 pages are not stored in the main memory because it is not demanded by the user. So if the user demands the pages of a process in the main memory, so we only shift these particular pages into the main memory, not the whole process. So this is the basic concept of the virtual memory. So in this particular example, we have F1, frame 1. Frame 1 is stored page 0 of P1, that is basically A0 of P1. And F4, page 2 of P1. Page 2 means that is A2. So A0 and A2 demanded by the user. So we stored only and only these pages in the main memory. Suppose we demand one more page, that is page P1. Suppose A1. We demand the page A1 of P1 in the main memory. So how we store that particular page in the main memory? So these are the procedural steps that I already explained orally. That is, first CPU generate the logical address of the required data. That data is in page P1 of a process P1. For example, we take a process P1, pages is stored in the main memory. So this is the complete written concept that I already explained verbally. So you have to just take this particular slideshow in the written form. So, procedure of case 1 and case 2. Case 1 explains the process of P1, page P1 is present, so it shows the validated 1, and it is the best case because it already stored in the main memory when the user demands. If page P1 is not present, so it shows an invalid bit, that is 0, that I already explained. Now, how we calculate the logical address space? So, basically logical address space equals to the frame number into the number of words plus displacement. So, this is the calculate the formula of the logical address space with respect to the frame numbers and the number of words plus displacement. Now, we move with the diagram that how we store the A1 of P1. This is basically page 1 of P1. So, how we store the page 1 of P1 in the main memory? So, first step, CPU just check in the PMT of page PMT of P1 that page is stored in the main memory or not. If it is not stored, so this page we have to take from the secondary memory and put into the main memory and entered the frame number into the PMT of P1. So, how we do this? First, we check in the PMT that page is not present in the PMT. Then, second step, we inform the operating system that this page is not present. So, it is known as a page fault. So, operating system authenticate that the demanded user is authorized or not authorized. If it is authorized, then take the page from the secondary memory, this page of P1, that is A1 page of P1 we take from the secondary memory and put the copy into the main memory. So, we have a space in the main memory, that is the F3 space is free in the main memory. So, we put the page A1 of process P1 into the main memory. So, this is comes in the frame F3, and this particular entry we have to update in the page map table of P1. I think it is clear enough to all of you that it is clearly explained that how we have to store any page of any process that demand by the user and is stored in the main memory, and how we have to enter that particular page in the PMT. So, this is the total concept of the virtual memory, ki how we have to swap the page in the concept of the demand paging, because demand paging also give the concept that we have to demand a page, not a process, not a complete process. We demand the page. So, we have to put the page in the main memory, not the process. So, we have to execute a bigger size of the process in the main memory. So, this is the basic concept of the virtual memory. Now, the advantage and disadvantage of the virtual memory. First advantage is that large virtual memory, we already explained that we have to put the large process as compared to the size of the main memory is lesser than the size of the process. More efficiently use of that memory, because we have use the concept of the demand paging. So, we have to swap it in and swap out the page from the main memory. So, we take the advantage of that particular concept. So, there is no limit on the degree of multi-program, because we have to change the page according to the user demand. So, this is the these are the advantages of the virtual memory. Now, the disadvantage of that, number of tables and the amount of processor overhead for handling page interrupts are greater than in the case of the simple page management technique, because this problem creates because the page demand are very frequently, and at each and every time we have to change in the PMT, change in the main memory. So, this creates the overhead in front of the management. So, this problem creates a page management problem with the overhead of the processor. So, these are the this is the disadvantage of the virtual memory. Now, the effective access time, because effective access time means we have to find the page. First, we have to find the page in the PMT, means it is the main memory. If that page is not present, then we take the page from the secondary memory to the main memory, and also also we have to check the in the PMT also in the page map table of the process P1. So this defines the effective memory access time. So effective memory access time is a process to calculate how much time taken by the operating system to swap out the demand data from the main memory and hand over the control back to the user. That means the user demand the page, this particular demanded page we have to give to the user or not. So this is the complete the effective access time. So this is by the EMAT, that is P. P represents the page. If the P is 0 means no page fault, P is 1, that means we reference from the secondary memory and put the take the process to the secondary memory and give to the main memory. So this is the basic effective access memory access time formula. Now we take a numerical. If the size process size is 4 KB and the main memory size is 8 KB. So in this particular example, the process size is lesser than the size of the main memory, and the page size is always same as the frame size. So page size is 1 KB and each page contains the 4 words. So how we have to calculate the new process of main memory that can be mapped from the physical address space to the logical address space. So if we calculate the logical address space, suppose in this particular example we have to calculate the data for C. So how we have to calculate the logical address space for the content C? So C belongs to the page number 0, and first we have to check the PMT. So page 0 belongs for the which frame number? So page 0 belongs to the frame number 1. So according to the formula of the logical address space, it is frame number multiply the number of words plus displacement. So it belongs with the frame number 1 multiply by 4, because each page contains the 4 words. So 1 multiply by 4 plus 2. 2 is the displacement. Basically C belongs with the displacement of 0, 1 and 2. So according to this particular example, the calculation of the logical address space for the C is 6. So this is the actual numerical that comes in the exam in the concept of the virtual memory. Now we take the another example. Suppose the address space by the 24 bits and the corresponding memory space by the 16 bits. So this address space, that means give the address bits, that is 24 bits, and the main memory address bits are 16 bits. That means in this particular example the size of the process is higher than the size of the main memory, because the address bits are more process address bits are the more than the main memory address bits. So calculate how many words are there in the address space. This is same like that. If we have 3 bits address, so how many words created in the process? If the address bits are 3, so we have how many words? We have the total words of 8, 0 to 7. We have 8 words in the process. Same as if the size of the address bits are given, that is 24. So how many words we have? We have 2 to the power 24 words in the process. So this is the basic concept. First part is this: how many words are there in the address space? So we have 2 to the power 24 words in the address space if we have the address specified bits are 24. Now the second thing is what? That how many the corresponding address bits are 16. So how many words are there in that memory space? So because we have the 16 bits in the memory space, so number of words are 2 to the 16. So we have 2 to the 16 words in the memory space. Now the third thing is that if a page consists of each page consists of 2k words. First we have to find the number of words. Now we have to find we have to give that page consists of 2k words. So we have the total words of 2 to the 24. In these words we have 2k words in a page. So how many pages and blocks are there in the system? So basically we know about the total number of words. Now in these words we said that 2k words used for a page. So how many pages are there? So we know about the total number of words, and we know also that each page consists of 2k words. So just we have to divide 2k 24 divided by 2k. 1k equals to 1024. So that is basically 2k over 10. 2k over 10 and 2k. So that is 2 dot 2k over 10, that is 2k over 11. So we have 2k over 24 divided by 2k over 11. So we have total number of pages are 2k over 13. So we have 2k over 13 number of pages of that particular number of pages. Now number of blocks. So same as we know about the total number of words in the memory space, that is 2k over 16, and we know that the page consists of 2k words. So we have to calculate, that is 2k over 5. So it is particularly 32. So this is the numerical third. Now the fourth numerical is that a virtual memory has page size of 1k words. 1k means 1024. There are 8 pages and 4 blocks. We have 8 pages. 8 pages means we have the 8 page in a process, and 4 blocks means we have 4 blocks in the main memory. So according to the table, we have page and the block. This is the frame and the particular frame number and the block number. So page 0, block number 3, page 1, block 1, page 4, block 2, page 6, block 0. But we have total number of pages are 8, but the present information is only the 4 pages. So 4 pages are absent in this particular table. So you have to calculate the virtual address for those particular pages, those are absent in this particular table, because it known as the page fault. So how we calculate the page fault in this particular example? So we know about the page size. Page size is 1, that is 1024, and it is also so known that 0 to 1023 in the decimal form. So it is 0 to 1023 for the page 0. Same as we have to calculate with add 1024 in this particular example. So we start with 1024 plus 1023, so it is 2047, that is for page 1. Same as we start with the 2048 sequencing. With respect to 2048, we have to add 1023 over there, so it is 3071. So these are the complete virtual address table in the decimal form, that is 0 to 7, because we have the 8 page and we only find the addresses for page number 2, 3, 5 and 7, because these pages are absent over there in this particular table. So we have to calculate the page fault addresses. These page faults are 2, 3, 5, 7. So just 2, 3, 5, 7. These addresses we have to just put in the answer. So these are the complete concept of the virtual memory. I think it is clear to all of you. Thank you.